I am glad all of you decided to come here on a Friday night to listen to me talk about what I'm calling printable electronics and the future of Southern Open Hardware. And then the subtitle of the talk is how to print Southern Arduino, because that's the question everyone always asks, and that's really what everybody wants to know. So first, just a few things about me. I have what I will call a distinct speaking style, which is code for I have a stutter. So I may take a little while longer to say some things. I may stumble on some words, but we can all get through this. I'm a fifth-year EE PhD student up at Columbia University. I'm my lab's kind of resident hardware hacker, which is why I'm still a fifth-year PhD student and I haven't graduated yet. And a fun fact about myself, I honk jars. So just a little bit about about my lab. It is called CLUE. It is the Columbia Laboratory for Unconventional Electronics. So the theme of our lab is novel integration of all of these kind of different technologies to build new and cool systems. We have a very entrepreneurial emphasis in the lab. We have 3 startups coming out of the lab, which is something we can talk about later. And something else I wanted to mention is that we're always looking for new students and new collaborators. We have a bunch of really cool tools that we have in the lab that we would be happy to share. So I'll just go through some of these slides really quick to give you kind of an overview of some of the projects that we do. This is my main project right now. These are energy harvesting active network tags. These are like smart RFID tags that are able to harvest energy from their environment, and they form a wireless mesh network, so they can be kind of the backbone of the Internet of Things. And really, all of this is possible because we are bringing together all of these kind of disparate technologies into a single package. This is one of the startups that we're working on. This is where I am going to be working starting in the fall. This is the technology that is going to make wearable heads-up displays bright and efficient. So our hope is in maybe the next 2 or 3 years, you will see this kind of technology, so then the Google Glass style of devices. How I actually got started into this whole open hardware printable electronics area is, so we teach a course at Columbia called Modern Display Science and Technology, and it's all about the glowing rectangles that we all spend so much of our day staring at. We have a series of lab exercises there, and we are now in the process of converting those into kits that will let anyone build their own kind of displays at home. And so then taking this to the next level, some of the projects I've been working on when I was an intern at Microsoft research was looking at ways that you can combine the 3D printing, rapid prototyping technology with these new printable electronics, so you can make a new class of objects in your 3D printer. But I think what I learned from that experience is that there's still one key component that is missing from all that. So I want to talk about these 3 things here to show how you really need need to have 3D printing, unconventional electronics, and kind of the missing piece of of open source hardware that is going to make this all possible. It's just a little overview. How many of you were here for the talks this morning about some open source hardware? How many of you know what open source hardware is? So it's a pretty self-explanatory thing. It is the open source software principles, and it is just applied to hardware. If you want to learn more about it, September 27th here in New York City is the Open Hardware Summit. You should definitely come and check it out. There are a lot of people doing some really interesting stuff in open source hardware. I just have the 3 New York City-based companies here, just in case there's anyone from the audience from these companies. And so I just want to say why I think open source hardware is important. So it's essentially, if you can't actually open up your hardware, you don't really own your hardware, and I think that's a very important cultural point to make. All right, 3D printing. Who knows what 3D printing is? Pretty much everyone. If you don't know what it is, you can go downstairs to the second floor. Stop by the MakerBot table, and they can show you how it works. But so then, how the MakerBot works is shown on the left, where you have a plastic filament, and it just moves along, spitting out the plastic, and it builds up things layer by layer. And there's a new very exciting technology coming to the DIY 3D printing scene, which is this stereo lithography based on a UV curable resin. So you have a vat of the resin, then you have a light source, and then you are able to expose the resin to the light source to get the pattern that you want. Some examples of some of the really cool things you can do with 3D printing: you can do large-scale things like the body of the car. You can do small-scale things like the nanoscale church. You can do food. You can do blood vessels. You can do clothes. You can do practical objects. You can do a whole bunch of really cool stuff. And this has a lot of people really excited. They are saying 3D printing, it is going to change the world. And yes, certainly it does have the potential to change the world. But there are still some key kind of elements missing from the current 3D printing landscape. Since if you look at most of the stuff you can print, so it's what I would call structural objects, not like functional objects. So you can have plastic in any shape that you want, but if you want something else, that may or may not be possible. So I am proposing that the solution to this problem are unconventional electronics. What I'm calling unconventional electronics are just any type of electronics that are not silicon based. So if you look at the kind of standard silicon, so it's all about making things smaller and faster. So following Moore's law, so you can cram more transistors on a really small space. But you can certainly imagine some applications where you may want large area electronics. You may want foldable electronics, stretchable electronics. You may want to have something that you could print out on a sheet of paper, and that's just not going to be possible using the conventional silicon electronics. So some example of what you can even do now with these unconventional electronics, you can have a solar cell on the right, you can have a display, you can have a battery, you can even do a whole bunch of exotic kinds of materials. And then the top left, that is actually a complete microprocessor, which is made using organic transistors. So it's a really promising technology. And so you can certainly see how if you have printable electronics that you are able to print out on your own, that it is really going to change the way that we design consumer electronics when you have a hardware update that is the same as a firmware update. So, so I think that this is where all of us really hope that all this stuff goes, to the Star Trek style of you can have anything that you want anytime that you want. Okay, that is great. I've been talking about the future. It's going to be wonderful, but seriously, how do we actually start with just printing something such as an Arduino? Okay, who knows what an Arduino is? Great. So, so mostly everybody. So if you don't, it is a really simple, really easy to use electronics prototyping platform. If you actually look kind of under the hood, all it is really is it's just a user-friendly kind of dev kit for an Atmel kind of microcontroller. And if we take a look at this at this piece of open source hardware, you can see that it's not really fully open. You have open source software, you have open source layout of the board, but if you actually want to get inside of the microcontroller itself, so it's a black box. It's a literal black box. So then why is why is this a problem? First off, as I said, it's a literal black box, and it's also something that you can't build on your own. So I'm calling that the pencil problem, which is based off of the essay that says it is not possible for a single person to build something as simple. So then even as a pencil, so then what chance do you stand to actually make a microcontroller? From a more practical perspective, if you need to use a certain microcontroller for your project, let's say the standard kind of Arduino has 20 pins that you can use. If you want to use 21 pins, you have to move up to the whole next level of the chip that it maybe has 40 pins or something, and so you're just wasting the pins there. So then another practical problem is since these are all from the same supplier, if there's any kind of disruption of the supply chain, you aren't going to be able to get the parts that you need for your open source hardware, which of course leads to a second problem of the possibility of having this fake hardware. SparkFun had this problem when they were trying to source some of the microcontrollers from, let's say, some shadier kind of places, and they got one of these chips. One of them is fake, one of them is real. If you can tell the difference between the two, you probably have already read, can read their article, but they look exactly the same. There's no way to tell. So, so then what I am, what I want to suggest is that if we do actually want to print on Arduino, we need to have an open source microcontroller. So let's start at the beginning. What is a microcontroller exactly? It is just a small scale computer, so you need to have a processor core with a CPU and an ALU in it. You need some memory, and then you need some inputs and outputs so you can talk to the real world. How a microcontroller actually works. So it just has a series of instructions that it is able to run, and that is defined by the command set. But so then what actually makes it go are millions and millions of transistors. Yes.
Why are you moving from Atmega to AVR?
So then this was just like data sheet that I was able to find that it that it had a nice nice like graphic of it.
When you say open source, I'm not able to understand. I mean, every microcontroller gives you all what you need, for example, processor, memory,
Yes.
all that stuff.
Yes.
What is it that you want to do beyond that you really want to open source it? I'm not able to understand.
So then
Can you repeat the question?
he wants to know what part of the microcontroller I am hoping that I hope to kind of open source here. I actually want to have the ability to actually build my own from the ground up. And if you look at what is on the inside of microcontroller, it is just millions upon millions of transistors all arranged in a certain way. So this next part, I'm just going to skip through kind of fast because nobody wants to have a physics lecture on a Friday night. Hey, okay, I stand corrected. But okay, all you need to know for this little introduction to transistors, you can think of it as a 3-terminal kind of device. So you have a source, a drain, and a gate. The current between the source and the drain is controlled by the voltage you apply to the gate. And for standard CMOS technology now, you have 2 types of transistors which are complementary transistors. So you have an N-type and you have a P-type. So you have one of them which is turned on when you have a high voltage on the gate, and one of them is turned on when you have a low voltage on the gate. How do you actually make these transistors? I'm not going to go through all this. If you want to know more, this Sunday there is at 12 o'clock right back here, there is going to be a pretty cool talk going through the whole process. All I want to say here is it's a very long, complex process, additive and subtractive. And it involves some really expensive equipment and also some really hazardous chemicals along the way. So, as I said, how do the transistors actually work? You can see here for the, I believe this is an N-type transistor. When you have the gate voltage less than the threshold voltage, you will not have a channel that is between the source and drain. Once the gate voltage exceeds exceeds the threshold voltage, you will turn on the transistor and you will allow it to conduct. So if we have these transistors, we are then able to start combining these switches into something something useful. So if you combine these two transistors like so, you can make an inverter. So for example, when you have A is low, it is going to turn on the top transistor. You'll see the high at the output. When A is high, it'll turn on the bottom transistor, and you'll see the low at the output. You can then start to build up more complex logic gates in the same way, and then you can actually start to build these kinds of logic gates using the actual transistors. So then just a note on how you would design something like microcontroller that is made up of all these logic gates. You can either use a hardware description language like Verilog or VHDL, where just saying how the gates should be hooked up. Or you can actually do the layout yourself, so in Silicon. So then this is all showing the VHDL for a full adder, and it's showing the Silicon layout for full adders in 3 different Silicon technologies. If you want to get started in this circuit design area, Cadence is the tool of choice, but it's expensive. There are some great free tools that are part of Fedora Electronics Lab. So if you want to start playing with that, that's a great starting point. Okay, legal issues. I am not a lawyer, so all this may or may not be. So all this isn't legal advice. All I want to say here is that there are multiple layers of legal protection for most of these kind of integrated circuits. So there's even a special kind of mask work which protects the Silicon layout. There have been patent disputes over features that are in the ICs. And so the last thing that I want to talk about is for a lot of these kind of technologies, if you even want to get started trying to design any of these ICs, you need to sign an NDA if you want access to the tools. So here's an interesting example. This is the first commercially available microprocessor. This is the Intel 404. The schematics and layout, they are available online, but I'm not sure if it is even legal for someone, if they wanted to start their own fab, to use this as a design they could sell. Fortunately, there are projects who are working on these open source kind of microcontrollers. This is from the Open Cores project, where they actually do have a full processor based on the Open RISC architecture. They have shown it working on an FPGA, and they are now trying to raise money so they actually make these on a silicon chip. So this is hard because if you want to actually compile silicon source code, you need to have your own fab. And fabs these days cost a whole lot of money. So the newest one opened up by Global Foundries not too long ago cost $4.6 billion. So it costs a lot just to get into the game. Fortunately, there are some projects where there have been some people working at home to see if they can fabricate their own transistors. Jerry Ellsworth was, to my knowledge, the first to demonstrate a working silicon transistor made at home, and then other projects such as the home CMOS project, which are kind of following in her footsteps to bring DIY silicon to the masses. So, I would say that if we want to truly open source the Arduino, we aren't going to be able to do that in silicon anytime soon. So we really need to reimagine what we want out of the Arduino. Yep.
Printing and Arduino.
Yes. So the question is, so what do I mean by printing? So then Arduino, so what I mean by that is you have a machine of some sort, hit a button, and it spits out. So then it spits out, the Arduino for you. So, so that is kind of the long-term goal here.
Can't you use an FPGA to do that also, rather than taking a silicon? Waiting till that time, in the meantime, use an FPGA to plan out the open risk.
Yes, yes. Certainly, you can use something like an FPGA, but if you don't have your own kind of machine that is able to spit out an FPGA for you, then you can't really call it a fully printable version of the Arduino, and that is kind of far off, kind of futuristic, but I think it's a goal that is worth striving for, goal that is worth thinking about how would we actually make that less of a dream and more of something that we could actually do. So hopefully I have convinced you. Silicon is hard, but there are other semiconducting kind of materials that are out there, that you can use to make transistors. This is a figure from my advisor's book. If you want to know more about it, that is certainly a great place to start. But so what I want to show here is this can be a completely additive process, which would be nice because having just an additive process pairs well with something like 3D printing, which is itself an additive process. Still, so now I don't want to give you the wrong idea that that we're gonna turn around and start to print out this kind of stuff tomorrow. This is still a very active area. So then if we can research and it still needs some help to get out of the lab stage and get more to the masses. And so one of the problems that I want to highlight here, so it's the use of the materials that you have to use. You have some really weird, really kind of exotic things we are using in the lab, and that really doesn't fit with the open source kind of mentality that pretty much any kind of material that you get should be safe, should be easy to use, should be kind of easy to source. If you look at this Active Ink N3000, if you want to buy it, you actually have to sign an NDA, and you are not allowed to publish any of the results that you get with something like this if you don't have their explicit okay. So, so then when I was saying you can pair this kind of fabrication of organic electronics with the 3D printing technology. If you think about a 3D printer, all it is a three-axis CNC machine with a plastic extruder head. So you can definitely see, well, hey, what if instead of having a head that extrudes plastic, I have a head that extrudes wire, that extrudes a low melting point metal, or if I have a pen loaded up with some of the inks that I want to print, then you can start to use your 3D printer to print electronics. And then something else that we need to think about, trying to design an entire open source microcontroller, that is going to be hard. But for a lot of projects, having a microcontroller is really not even something that you need. So you can think about doing things in software. We can go back to the old days where you were doing more of the stuff in hardware. So then final kind of point to make is, so we have a good way to share objects. We have a good way to share hardware schematics. We have a good way to share software source code. How do we share something that is going to have all of those in a single file that you can send to some kind of printer that is going to be able to load it all up into one and spit out the object that you want? So I have rambled on enough. Hopefully, I have gotten you excited about this, about the combination of the three technologies and and all the possibilities they can open up. So now I'd like to open it up to any questions. Thank you very much. Yes.
The research that you mentioned,
Yes.
what's the density like in terms of the amount of transistors that have been printed in a particular area?
Okay. Yes. So the question was about the kind of densities of the printed transistors we're able to get. Currently, if you look at silicon transistors, they have a gate length of, I think it's 22 something nanometers now. We have the gate lengths of about 1 to 10, so the microns. So we are large. So large area transistors, large area electronics.
That's about what happened before, right?
Front here.
How do you actually print them out? Do you use like screen printing techniques, or how do you manufacture them yourself? How do you put them together?
So the question is, what are some of the manufacturing techniques that we use to build these sorts of electronics? Some of the materials we are working with can be screen printed on. Some of them can be printed using inkjet kind of printing. Some of them have to be deposited using spin coating or some other more traditional kind of equipment, but so we're always looking for some ways to kind of transition all these steps to be just something like an inkjet printing step is kind of what we're going for.
Has there been any success with creating PCBs? The printed circuit boards?
Yeah. Yes. So if you look at this example here, this is essentially a 3D printed robot chassis with the with all of the traces kind of printed into it. So you can definitely get something like that. So one of the limitations of it now, all of the traces are on the same 2D plane. So it isn't actually possible to have it go like yet. But I definitely think that is something that's going to be coming. Thank you.
Two questions. What in the last process you were talking about? What's the kind of voltage area you're running at? And then the second would be what's the most interesting thing you've done with that kind of stuff in the lab with it?
Okay. So the voltages for the transistors that we normally work with for a lab need about 40 volts. So it is certainly possible to lower that voltage substantially by using newer sorts of material. As to your second question, the most kind of interesting thing I have done in the lab. So it was actually this so the photo there on the far right, which is using a which is using the unicorn pen plotter MakerBot kind of attachment to print some of the layers for a printable transistor. Yes, thank you. A constructive use of a laser pointer from the audience. I appreciate it. Keep them coming.
I want to know how, if one wanted to make an open source microprocessor,
Yes.
how do you get around the patents? Because between Intel and AMD, and both of them have pretty much bought every single company that's ever tried
Yes.
to get into that space. I would imagine the open source view would just, their view on open source would just be sue them to death.
Right. So I think you are probably going to have to take a similar kind of approach to the 3D printing kind of community. If you look at all of the basic patents for 3D printing, those were from the 70s. Those are now they have expired. Something like what we can do, we can go back to the 1970s era, and it's not going to be the greatest technology, but it's going to be an open source microcontroller. Yes. Yes. So the question was on if it is possible to print some sort of memory, and so the answer to that is yes. There are plenty of groups working on printable kind of memory cells based on these same kind of organic electronics. And so they do have some that are able to kind of operate at the standard 3.3 5 volt 5 volt levels if you wanted to kind of interface this stuff with standard electronics.
How fast are the transistors that you're making now?
We are we are making transistors that are probably in the tens to hundreds of kilohertz range. So then, as I said, these kind of unconventional electronics, they will complement silicon electronics. They certainly aren't going, to replace silicon electronics. Yep, sorry, I can't see with some of these lights.
Obviously, the passive components like capacitors and resistors, some type of printing technology would work very well. Semiconductors, obviously, the hard part to work
Yes.
with. Yeah, as you said. Are you familiar with any other technology, like say zinc oxide, making semiconductors through an additive process?
Yes. So I know of some groups who are working on using zinc oxide, down so like Princeton, but it's not something I am actively involved in, so I couldn't really comment on it intelligently.
Given that a couple of the specific specs you've mentioned have been pretty close to the Intel 4004,
Yes.
how close would you say you are overall to being able to do something with about the same functionality as the 4004 right now with what you have in the lab?
So then as I had had a few slides back, there have been some of the research groups who have shown these who they have shown these 8-bit kind of microcontrollers that are made out of the same these organic sorts of material. They hadn't used any printing techniques in order to make it, but it is certainly showing that it's possible. Yes. Yes. So the question is, how do you print the oxide layer for the gate, where you need to have a very specific thickness for the gate? For something like that, we have been using screen printing, kind of techniques because that is useful for larger areas. It ensures uniform coverage, and it's a good way to control the thickness of the layer. Yes. Yep.
So I'm curious what you were working with, one, and two, is recycling of materials something that's kind of in the back of your head? Once a circuit may have outlived its useful life.
Yes.
Would it be something, to be able to take that and then recycle it and reuse it again?
Right. So the question is on the use of, the materials and their toxicity and their recyclability. How organic electronics, so they get their name, is so then these are all mostly carbon-based, sort of compounds. And, something we are working with actively in our lab is to use graphene and carbon nanotubes for these, for some of the layers of these devices we are making. So certainly even at some point in the future, you could even see having all carbon-based electronics, so you don't have any of these crazy chemicals that you have in all of the electronics now. Have I played with the light scribe etching stuff? No, I have not. So then what is special? Oh, yes, yes. So then, yeah. So what the question is about there has been some work showing you can use the laser source from a light scribe DVD drive to build supercapacitors. So then certainly you could start to look at using that to build other types of devices as well. Are we done? Sorry, yeah.
Thank you for pointing my thoughts on it. I'm doing the dark right now. What's your yield on these? Like, what percentage of them work when they come out?
Our yield is if I get 10% yield, I am happy. I am ecstatic. Yeah, yeah, yeah. So yeah. Certainly, since this is just like research lab, so then a research scale. If I have a substrate where I'm making say like 40 of these, if I can find find one of them that works, I'm happy. I'm done. I've done what I wanted to do and show. Any other questions? Comments? All right.